The following program is brought to you by Caltech.
Our next speaker is going to be Torrence Johnson, and he's an expert in the geophysics and geochemistry of the satellites of the outer solar system. He's participated in all of JPL's major missions to the outer solar system, both as a researcher and a scientific leader. He was a member of the Voyager imaging team and NASA's science definition teams that developed the concepts for Galileo, for which he was a project scientist, and Cassini, where he's involved with 2 experiments. He's currently the chief scientist for the Solar System Exploration Directorate at JPL, where his responsibilities include program development for future exploration missions.
Okay, well this talk's going to have a rather different flavor than Hal's. What I'm going to do is kind of just take a personal look at the history of things that have driven our missions and to try to explain things like test theories, such as Hal's been talking about, the ones that preceded that and the ones that will probably follow that. And to take a look at what, I'm not going to tell you what we found out with each mission. I'm hoping that Jim Bell's talk will tell you a bit about the physics and characteristics and physical properties, the objects we're talking about, and we're talking about primordial bodies. I had sworn to myself I wasn't going to give you my speech about the theology of primordialism, but I couldn't resist after I saw the front page story in the Times this morning about finding more carbonaceous chondrite materials from this latest fall, and these things being witnesses to the early history of the solar system and so forth. There's a thread that runs through the discussion of how you go about promoting your science and getting funding for missions and research on these primordial bodies. Since they don't look like the Earth and they're therefore not interesting to some of the people that worry about Earth-type things, there's been a tendency toward what I call more primordial than thou thinking. Is that if you can't claim that it's an interesting object like the Earth, you're going to claim that it is the most primitive thing that you've ever seen, and it shows you what happened 4.6 billion years ago exactly. And that's kind of interesting because that thinking still goes on, even in spite of the fact for the last 20, 30 years, we're getting increasing evidence that most of these things are not primitive in that sense. They've gone through tremendous histories, dynamical histories, thermal histories. We're now thinking about these things as starting off with relatively big bodies and so forth. And yet it's sort of interesting that the way we're describing this to people still goes back to, well, this object was unchanged from 4.6 billion years ago. It came to our doorstep, and now we know what formed the solar system. It's this thing here. That type of thinking actually goes back to discussions about how you go about deriving missions and so forth to study these things. I'm not going to stick to this rigorously, but the discussion that I'm going to give you falls back a lot on the issue of what do we actually know about the things we have here on the Earth, and how can we relate those things to the objects we see out in the solar system, asteroids and comets primarily. Although, as you're probably well aware, there's basically a continuum of things between things like asteroids, comets, what we call planets, what we call small planets, what we call dwarf planets, what we call Kuiper belt objects, etc. And they've all gone through these histories, and they're all subjects of great interest for possible missions and have been in the past. I'll mention a few highlights of things we've learned from some of the missions we have had that have affected our trajectories of thinking about how we go about exploring these things. And finally, end up with a few comments connected with this workshop, which is, I think this whole history, to me, drives a need for new techniques to understand these objects that we don't have now. We've had lots of missions to small bodies now, and we know wonderful things about them. We don't know a lot of things that actually relate to this first line there. And it's probably impractical to have a sample return mission from even every class of these objects we can now define. So we've got a major exploration issue there. So I said the theology of primordialism sort of affected things from the beginning in the thinking about missions to these things. If you go back to the beginning of the space program, first thought about primitive body missions was we don't need them at all. And that was sort of promoted by one of my heroes, Harold Urey, one of the founders of modern geochemistry and cosmochemistry. And he remarked a number of times when asked about the value of the Apollo program, for instance, we don't really need missions like this. We have samples of cosmic material delivered to our doorsteps free of charge by God in the form of meteorites. In addition to that, there was an obvious thought that early dynamical thinking was that things like the asteroid belt were in a collisional state. You look at populations of things grinding themselves up, and therefore there was a strong feeling that, promoted not just by Urey but by many others, that the continual cosmic infall of material would cover the moon and most other objects that didn't have other processes going on them with the most common type of meteorite, chondrites. And that's all we would see. In fact, I had very interesting conversations in that era with astronomers up at Palomar and Mount Wilson when we were beginning to take a look and see whether we could make observations of asteroids and see whether there were differences amongst asteroids. And their answer was more or less, well, why are you doing that? It's quite clear that that's just all ground up meteorites, and it'll all be the same stuff covering every body that you look at. And if you told them that there were some of these objects that didn't look like that, they say, well, those must be unusual. There's something special. So there was a feeling at this point that you'll just see chondrites every place. And that actually persisted through more or less the Apollo era. Of course, the Apollo results, Urey had an interesting codicil to this thing, saying, well, we got the samples from the moon back free of charge, delivered to our doorsteps by NASA. The important... yeah, you can take the political theology and... The obvious thing, of course, was that the primitive moon was not primitive, and it was also not chondritic. And that began to at least allow people to talk about going out and looking at these things like asteroids in a different context, that they might possibly be different than just an object of whatever type covered by chondritic dust. And that this slide encompasses about a decade or a decade and a half worth of expanding telescopic capabilities of understanding what was going on in the asteroid belt. The early spectral surveys, I'll show you just a couple of pieces of that. This mostly attached with Clark Chapman and his colleagues, show that there was a great spectral diversity amongst the asteroids. Albedos of the asteroids were not only different than chondrites, they're mostly very, very dark in terms of numbers. And that was understood early in the 1970s as a result of work that got started with Dennis Matson's thesis, for instance, and then got carried on with surveys of albedos of objects. The connections to meteorites, the work started by Mike Gaffey, Tom McCord's colleagues, and various other people, where spectral and albedo started being connected to asteroids and trying to make this link. Comets during this period of time, although they were still regarded as, quote, dirty snowballs, there is a feeling, particularly among comet observers, that they had to be all big chunks of ice, basically, even though they should, of course, in some sort of cosmic proportion, have about a 50% ratio by mass of rock and metal as well. But there was observational data occurring at this period of time that indicated strongly that comets also had very low albedos generally. Distribution of asteroid types with astronomical astronomical unit, astronomical distance from the sun, heliocentric distance. That was an outcome of all of these albedo and spectral studies, and indicated that there was regularity in spite of the feeling that there ought to be mixing of some sort. This is still an issue that Hal alluded to in terms of one of the observational constraints. We don't see everything, every place mixed in equal abundances, and that's an interesting thing to consider. And mission studies at this time started looking at the results of these astronomical observations. In fact, one of the very first asteroid mission studies that I worked on with Refriger finale was, in fact, a Vesta and Ceres flyby pair in order to try to understand why these two objects, two of the largest asteroids in the asteroid belt, are so different in spite of more or less being in the same vicinity out there, and what their evolution was. We didn't get a real primitive bodies mission, however, until finally after, there was a period of time here when I probably wrote more proposals for failed comet missions, failed asteroid missions, and things like that than most of the current generation have ever had a chance to look at. None of them worked, at least for the US. We've finally got one with the European Space Agency and their Giotto mission. Let me just, this is just a little bit of interesting history. This is a page from the draft paper that was submitted on the Vesta connection with HED meteorites, in this case specifically a eucrite, and a figure of the spectrum from ultraviolet to 1 micron there of Vesta. The points are from 2 sets of data runs, and that happens to be, I think, Nuevo Laredo, a basaltic achondrite. And reflectance spectra started to be put together with both albedo and spectral features, showing that there was, in fact, quite a range of the large asteroids. This then became a taxonomic playground with albedo, spectral features, and so forth, generating a situation now where we have asteroid taxonomy that comes embarrassingly close to having a separate astronomical taxonomic type for every asteroid. There's a lot of variation out there. Over there is a figure you don't see much these days from Dennis Mattson's thesis that shows the things he observed in his thesis, and albedos here are all well below the chondritic range that was known at that time, just from laboratory measurements of chondrites, and some things were extraordinarily black, and that was one of our first indications that very, very dark material indicated was out there. Okay, so the first primitive body mission was Giotto. In spite of the fact that everything looks bright here, of course, in these high phase pictures of the scattering on the surface, actually, as Giotto found, the nucleus was in fact coal black. It was our first in situ study of cometary particles, indicating many of them were in fact carbon rich, the so-called Chan particles, carbon, hydrogen, oxygen, nitrogen rich particles. Also got the first in situ D to H ratio that was non-terrestrial, and that's still an issue of comparing these types of primitive bodies with what's going on in the inner solar system. Okay. Asteroid visited by spacecraft. When I found this on Wikipedia, even though I was involved in a number of these things, I was stunned by how many of them we've actually visited now. This is arranged, I think, by date. Yeah, these are the first ones down here. Gaspar was the first asteroid visited by a spacecraft. Most recent one, of course, is for Vesta that we're in orbit around at the moment and getting ready to leave to head to 1 Ceres. So that we have had encounters of various sorts with a lot of these asteroidal materials now, asteroid objects, both NEOs, main belt objects, and in the case of Ida, a moon of one of these asteroids. And this is just to give you a little bit of trip down memory lane. Galileo, Galileo visited Gasper, an S-type main belt object. Ida, also an S-type object, and discovered a little dactyl sitting there outside of it, which also gave us the opportunity to estimate its mass and therefore its density, which was, at least within shouting distance, a density that was consistent with ordinary chondrites if you accounted for porosity. Near Shoemaker, actually orbited, flew by Matilda, a C-type object. This was one of our first hard indications that many of these smaller bodies had very, very low porosities. There was indications of this before, but that was, this was one where it was pretty clear you had to have a porosity of around 50% to explain the data for rational chemistry for a C-type object. First orbiter lander on Eros in 2000, and also gave us a good close-up look at the regolith at very fine scales on this object. Okay, Deep Space 1, first ion drive planetary mission, went to Comet Pirelli and started us with another set of looks at comets that showed quite a wide variety of different types of surface features, and also a very low albedo in this case. Something that was beginning to be noticed by this point was there didn't seem to be this sort of model that grew out of the thinking of, that started with Whipple's icy or dirty ice ball model, that you might have a low albedo lag deposit, and what you were seeing with jets was something had punched through the surface. And so we were sort of expecting in this era to see dark objects which had big holes punched in them where you had ice exposed. People used to make measurements in laboratories to try to explain cometary jets that way. Stardust, major factor, and this is our first cometary sample return, basically, rather than in situ measurements. And I think most of this audience is well aware that the major finding here was that stardust was perhaps the most oxymoronic name we've ever given a spacecraft, since it is very, very difficult to actually find stardust in the stardust samples. What we found instead was a lot of refractory materials, but things that apparently formed in our own solar system and were mixed into the mix. This is an olivine grain here, obviously formed at reasonably high temperatures. Got a lot of interesting information on the flyby comet, also Wilt-2 at the same time. Deep impact, in addition to these spectacular impact pictures, which gave us a lot of information about the physical properties of the surface and some about the chemistry, one of the things that they did was to, I think, start solving this mystery about where the jets and cometary gas emissions and so forth actually come from. Again, this surface is more or less entirely coal black. This false color picture here shows in blue areas that have just a little bit of water signature in the spectra. Not raw water on the surface, but just a little bit of water in the surface. And the interpretation of this is you've got to have water from underneath that's coming up as a result of being driven up by a thermal wave and getting out, but it's not coming out of big holes in the rocky crust. And if any of you heard Joe Ververka's talk at the AGU this last year, the relook at these various areas on Temple 1 by Stardust Next is sort of confirming that picture of how the cometary jets actually occur. Stardust Next, as I say, flew by, and the jets that were geometrically pinned to this, if I remember Joe's talk correctly, seem to be coming from the edge of some of these scarps here. And again, although this, of course, is photographed in order to show surface features, if in reality this whole surface is effectively coal black. Okay, Hayabusa can't be ignored here. First S-type NEO sample return. We got little pieces of this back according to the latest analyses that I have seen. Very gutsy mission. They had a lot of trouble getting the sample back. It did not work exactly as they expected, but they appear to have actual samples of this thing back. they also get the award for the best international wordplay, since there was a thing called Muses C that was a U.S. contribution to this, and they actually named this smooth area in here the Muses C. Rosetta, 2 asteroid flybys under their belt, including Latisha, a very interesting object with a much higher density than one might expect from its spectral appearance. And so the current speculation is that the Latisha data suggests that this, in fact, is a differentiated asteroid where it's got a higher density material underneath a fairly primitive crust. They're, of course, still on their way to this unpronounceable comet, the primary target, and hopefully we get a lot more information about what's going on cometary processing and in situ data and a lot of chemistry that we don't have. Okay, finishing up with the litany of the objects that we have looked at. Dawn is, of course, around Vesta now, and so finally the mission I worked on with Refriger finale over 30 years ago, finally they're doing it, and it's really absolutely fantastic to watch this. We're currently in orbit doing Vesta. We'll be leaving for Ceres shortly. An important part of what's going on in the Vesta data analyses, I've sat in both the LPSC and some of the European Geophysical Union, Geosciences Union meeting sessions, is that Vesta is well instrumented for chemical analyses, both spectral analyses and neutron gamma ray analyses. And the whole issue of the composition of Vesta compared to these meteorites we have on the surface that we have linked to things with small chunks of asteroid that are moving into the various resonant areas in the asteroid belt called Vestoids that Rick Wenzel has looked at for some years. That link seems to be pretty good. From what I'm looking at, I think by the time the smoke clears, there's going to be an even stronger link to the HED meteorites, the Howardite, Eucrite, and Diogenite meteorites. And so, in effect, that will close the loop back on this and effectively means that we have an effective sample return from a differentiated asteroid. And in fact, the analyses of the geophysics and geochemistry of Vesta that are going on based on the Dawn data now are being able to factor in constraints of fairly high order based on what we know about the geochemistry and characteristics of the samples from Vesta. Future missions, most of you know OsirisRex is going forward as a New Frontiers mission. That will be another NEO sample return, but in this case it'll be a C-type or at least a primitive type object. And Comet sample return is in the mix for the next New Frontiers call. And we're working at a number of places, working on trying to develop concepts that would make those things work in terms of getting the next stage beyond where we are now with the Genesis results. Okay, what have we learned? We've learned a lot more than I can just put on this chart, but primitive bodies span a range of different objects, evolutionary histories. The dynamical rearrangements of the solar system that almost surely occurred in some form, whether it's Hall's current model du jour or these things are all connected. You look at the exoplanets, this stuff happens. You can't deny Newton for too long. These things will happen in these systems when you put together these planetesimals. And that's now a major issue of putting together those histories, testing those models, and trying to see what we got. To me, that means we need a lot more geochemical information from these objects to try to pin down what their relationships are. We've got, many of you probably teach courses on meteorites. We can fill pages of meteorite categories of different types based on oxygen isotopes, based on their petrology and so forth. But we have damn all few places where we can tie those types of information to specific objects that have had some sort of dynamical history. And I guess the message that I've got then in thinking about going forward into this this workshop is to try to find some way out of that, other than just say we got to get a sample returned back from every asteroid or every asteroid family or every comet family, but to try to do this with a smaller number of observations, either remotely from the Earth or from space or in situ. And if you look at the decadal survey, just finishing up, if you look at what the small bodies and primitive bodies panel said about possible observations in the future in the decadal survey, they emphasize that type of thing. They're talking about, let's test some of these models by getting detailed isotopic composition for rare gases, et cetera, for a whole list of objects, which is at the moment effectively completely not possible from a fiscal point of view if you try to even do 2 or 3 of those types of missions. We have to figure some other way to collect the type of data to test these things. And so that's the end of my sermon. Thank you.